Picture this, right? It's Easter morning, the year 1900.
Okay, I'm picturing it.
You are standing on Fifth Avenue in New York City. You look up and down the street, and, well, what do you see?
I'm guessing a whole lot of horses.
Exactly. It is an absolute sea of horse-drawn carriages. I mean, you've
Right.
got top hats, cobblestones, and, barely a motorized vehicle in sight. The world is basically running entirely on oats and analog mechanics.
Yeah, the classic archival photo. It's a great image.
Right. So hold that image in your mind and fast forward just 13 years, just to 1913. Same city, same street, same holiday. You look up and down Fifth Avenue and the horses, they're just gone.
Completely replaced.
Yeah, entirely replaced by automobiles. I mean, in just over a single decade, the entire concept of human mobility was fundamentally rewritten.
It really is a stark visual reminder of exactly how fast a technological revolution can displace a dominant system.
It's crazy to think about.
Well, the contrast in those historical photos is jarring, right? The transition wasn't some slow, gradual phase out. It was a sudden, violent shift in infrastructure, economics, and just daily life.
Yeah, you need a magnifying glass to find a car in 1900.
And by 1913, finding a horse is the anomaly. It really serves as the perfect historical parallel for the threshold we are standing on right now.
Which brings us to the core mission for today's deep dive. We are looking at the next massive leap in mobility for you, the listener. But this time, the transition isn't about replacing the horse with the combustion engine.
Right. It's a completely different paradigm.
Exactly. It's about replacing the human brain with software. We are exploring how vehicles are making this monumental shift and, more critically, the sheer engineering rigor required to test these systems so they don't just crash in the real world.
Because the stakes are exponentially higher today. I mean, Henry Ford basically just had to prove his vehicles were mechanically reliable.
Right, that they wouldn't just fall apart on the road.
Yeah. But today's engineers, they have to prove their vehicles are cognitively reliable, which is, a vastly more complex problem to solve.
So to navigate the mechanics of how this is actually being done, we are pulling from a really fascinating presentation by Professor Josef Uchitina. He's at the Institute of Automotive and Transport Engineering at the Brno University of Technology.
Yeah, that's Alati VUT in the Czech Republic.
That's the one. And this institute is truly at the forefront of the virtualization of automotive testing. So we are focusing strictly on how ADI VUT in Brno is pioneering the digital twins, the sensor architectures, and the localized testing required to make autonomous driving a functional reality. Okay, let's unpack this.
Well, the fundamental premise of Professor Ichitana's presentation requires us to kind of abandon our traditional definition of a car.
How so?
The era of the vehicle as a static, purely mechanical machine ended years ago. The core value and functionality of modern vehicle are no longer dictated by its engine block or its transmission gearing.
Right, it's not just about horsepower anymore.
Exactly. The car has basically transformed into a rolling, continuously evolving software platform. Its safety functions, its driving dynamics, all of that is defined by code, and that code is updated dynamically over the air.
I mean, we've all grown accustomed to over-the-air updates on our phones or laptops, right?
Sure, totally normal for a phone.
But updating the operating system of a 2-ton kinetic object sitting in your driveway, that presents a totally different risk profile. The car you park on Tuesday might have completely different braking thresholds or like lane centering aggression by Thursday morning because of some overnight patch.
Yeah, the functionality literally changes while you sleep.
And to facilitate that level of continuous software evolution, these vehicles are just ingesting a data deluge that is honestly difficult to contextualize. The VUT Brno research points out that a fully autonomous vehicle processes 4,000 gigabytes of data every single day.
Which is staggering. I mean, for a sense of scale, the presentation equates that 4,000 gigabytes to the daily data consumption of over 2,600 average internet users.
Wow, over 2,000 people just scrolling and streaming all in one car.
Yeah. And all of that bandwidth is isolated within a single vehicle's local network over a 24-hour period.
And looking at the source material, it's so fascinating to see the hardware divide and how companies actually capture that data. Like, you have Waymo taking this total maximalist sensor fusion approach, right?
Yeah, they throw everything at it.
They equip their vehicles with 29 individual cameras, including infrared, alongside 6 radars and 5 LiDAR systems. The data throughput is immense.
I think the numbers were, 10 to 70 megabytes per second just for a single LiDAR unit?
Yeah, and the cameras are pulling 20 to 40 megabytes per second. But then conversely, Tesla takes a minimalist, vision-only route. They rely primarily on 6 standard cameras and 2 stereo cameras, and they omit LiDAR and radar entirely.
It's a completely different philosophy on how to solve the same problem.
But, taking a step back here, I kind of have to challenge the fundamental premise of this massive data load. We are talking about outfitting consumer vehicles with the computing power of a small server farm, processing gigabytes of raw telemetry every second just to, identify a stop sign or a pedestrian.
Right, it sounds a bit extreme.
Yeah. Are we just engineering a massively overcomplicated solution looking for a problem? I mean, is the average driver really asking for a $50,000 supercomputer just to run an errand to the grocery store?
Yeah, it is the exact friction point the automotive industry is grappling with right now. And, the VUT Brino research addresses that utility question directly.
Okay, so how do they justify it?
Well, the goal of this architecture isn't just to build a more entertaining luxury car for someone who can already drive perfectly well. If we connect this to the bigger picture, all of this data processing and sensor redundancy is in service of one definitive objective.
Right.
Professor Richitina's presentation frames this as the grandma benchmark.
The grandma benchmark. I love
Yeah.
that name. Explain the parameters of that for us.
It's great, isn't it? The presentation defines ultimate success with a very specific scenario. The quote is basically, assistive systems will help older people the most. Grandma gets into the car and says, take me to St. Anne's and park. That is real mobility.
Wow. So it's about total independence.
Exactly. The technology is only truly successful when it becomes entirely invisible to the user. It provides mobility to demographics that are currently locked out of personal transportation.
That reframes the engineering challenge entirely, doesn't it? It stops being about offloading the annoyance of a highway commute for some tech bro, and it becomes an accessibility mandate.
Yeah, exactly. The end user shouldn't need to understand sensor fusion or, LiDAR point clouds.
They just need the vehicle to safely navigate a really complex urban environment so they can get to a hospital appointment.
Right. However, reaching that frictionless end state requires passing through a highly volatile transition period. The presentation outlines the standard scale of automation.
Which goes from 0 to 5, usually.
Yeah, it begins at level 0, representing pure manual control. Then it progresses through basic driver assistance, like your standard adaptive cruise control, up to partial and conditional automation. And the grandma benchmark sits at the very top, high and full automation.
The problem is that the entire industry is currently just bottlenecked in the middle of that scale. We are basically stuck in the era of DCAS or advanced driver assistance systems.
Yes, the messy middle ground.
And the presentation highlights the specific regulatory and safety framework of DCAS Phase 3, which operates under this wild psychological paradox. The rule is basically, hands may be off the steering wheel, eyes must remain on the road.
Which is where the system inherently clashes with human neurobiology. I mean, the industry refers to the vehicle's safe operating parameters as its ODD, the operational design domain.
So the conditions where it actually knows what it's doing.
Right. As long as the weather is clear, the lane markings are visible, the traffic is predictable, the software handles the dynamic driving task perfectly.
But the moment the vehicle encounters an edge case outside its ODD.
Like a sudden heavy snowfall obscuring the camera lenses.
Yeah, the system basically just throws its hands up and immediately hands control back to the human driver.
Exactly. We are asking human beings to act as a system fail-safe, but humans are demonstrably terrible at maintaining high alert vigilance when they have absolutely nothing to do.
It's the equivalent of making someone sit as a co-pilot on a 10-hour commercial flight, right? You forbid them from touching the yoke or the throttle, but you expect them to flawlessly execute an emergency landing the millisecond a single red light flashes on the instrument panel.
Yeah, you are essentially setting the human brain up for failure.
So how do we fix that?
Well, that psychological failure point is precisely why the Institute of Automotive and Transport Engineering at VUT focuses so heavily on the human factor. If the vehicle is driving itself safely 95% of the time, the driver will naturally experience cognitive disengagement. They're going to zone out.
Right, they'll start looking at their phone or daydreaming.
To counter this, researchers are developing advanced DMS driver monitoring systems. Under DCAS Phase 3, just tracking the torque on the steering wheel isn't enough anymore because hands-free driving is permitted.
So they have to watch the driver's face.
Exactly. The DMS must track eye gaze, blink rate, and even microsaccades to actively measure fatigue and cognitive load.
But testing those physiological responses isn't something you can just do safely by putting a distracted driver on a public highway, right? You can't just wait to see if they crash during a system handover.
No, definitely not. So the researchers at VUT Breno utilize a driver-in-the-loop simulator, or DIL.
Okay, so like a really advanced video game setup.
Basically, they put human subjects into a heavily instrumented simulator to study the exact mechanics of their reaction times when the automation fails. The DIL allows them to engineer the escalation of HMI alerts, human-machine interface alerts.
Like the beeps and flashing lights on the dashboard.
Right, because if the software determines it is leaving its operational design domain, how does it command the driver's attention? A visual warning on the dashboard might be completely ignored by a driver who's looking out the side window.
Oh, that makes sense. So what do? Does the system trigger a haptic vibration in the seat? An auditory alarm?
Exactly, they test all of that.
Mm.
The simulator provides empirical data on which combination of localized alerts forces the fastest cognitive re-engagement, which hopefully prevents the driver from fatally over-trusting the automation.
Okay, so we have the human element isolated and tested in the simulator, but we still have to test the software's ability to actually drive the car. And just like you can't test human distraction on public roads, you can't test dangerous algorithmic edge cases in live traffic.
No, the liability would be astronomical.
You can't just program a test vehicle to deliberately swerve into an intersection to see if the collision avoidance logic holds up.
Right, which necessitates a complete migration from physical testing to virtual environments. And the foundational element of Quadi VUT Brano's research is the construction of ultra-high-fidelity digital twins.
Okay, digital twins, I hear this buzzword a lot.
Yeah, but here it means they build a true one-to-one mathematical model of the physical vehicle and its environment. By utilizing software suites like MATLAB, Simulink, and Roadrunner, engineers can execute millions of dangerous traffic scenarios in the cloud.
Validating the logic controllers without risking a single prototype or human life.
Exactly.
Well, here's where it gets really interesting, because looking at the source, the granularity of these digital twins at VUT Brano goes way, way beyond a basic 3D model.
Oh, absolutely. It's incredibly detailed.
They use a physical Skoda Enyaq IV60 as their baseline test vehicle. And to build the virtual twin, they utilize this specialized vector plus IMIC mix measuring system to monitor 25,000 individual variables simultaneously.
25,000, yeah. They're tapping directly into the vehicle's localized nervous system, the CAN bus architecture.
Because a modern vehicle doesn't have just one central computer doing everything, right?
Right. It has multiple controller area networks, or CANs, where subsystems communicate. The drivetrain CAN handles the critical physics, wheel speed, lateral and longitudinal acceleration, steering angle, and absolute pedal position.
Okay, they track the physics, sure, but the source explicitly notes they also monitor the comfort can. They track the ambient cabin temperature, the intensity of the HVAC system, and even whether the seat heaters and steering wheel heaters are engaged.
Yeah, that seems like overkill at first glance.
Seriously, why does the digital twin of an autonomous driving system need to know if the driver's seat is warm?
Because in an electric vehicle architecture, like the Skoda Enyaq, electrical load directly impacts thermal management and voltage distribution. Engaging the seat heaters creates a draw on the high voltage system.
Okay.
And that draw alters the thermal state of the battery pack, which can trigger cooling pumps, which then changes the available voltage for the primary compute nodes processing sensor data.
Wait, so turning on the seat heater could actually affect the self-driving computer?
Yes. In an environment where decisions are made in milliseconds, a slight voltage drop to a processing unit could introduce latency. The simulation tracks 25,000 variables because absolutely nothing in a modern vehicle operates in true isolation.
That is mind-blowing. So they extract those variables to ensure the virtual Skoda Enyaq behaves identically to the physical one. But simulating the car is only half the battle, right? They also have to simulate the environment the car's sensors are perceiving.
Exactly. And this isn't rendered like a video game. It's a physics-based perception simulation. They utilize a tool called ANSYS A Accelerate to calculate the actual physics of the sensor inputs.
What does that look like in practice?
Well, when the simulation generates a virtual radar wave, it actually calculates the Doppler shift of moving objects. It also simulates multi-path reflections.
Meaning, like, if the virtual car fires a radar pulse, the software calculates the signal bouncing off the asphalt, hitting a metal traffic sign, ricocheting under the chassis of a nearby truck, and returning to the sensor as a distorted signature.
Exactly that. It tests the software's ability to filter out all that localized noise. And they apply the exact same physics to optical sensors too.
So like cameras.
Yeah. If the scenario calls for rain, the simulation doesn't just draw some animated water on the screen. It mathematically calculates how water droplets physically accumulating on the curvature of the camera lens will refract ambient light and distort the image data.
Oh, wow. It's actually simulating the physics of a wet lens.
It is. It calculates thermal contrast degradation for infrared cameras during a simulated fog event. The digital twins algorithms are fed raw, physically accurate, degraded data to see if they can still identify a pedestrian.
And to ensure all of these disparate simulation tools can communicate seamlessly, the industry relies on ASIM OpenX standards, right? The presentation highlights OpenDrive, which mathematically defines the static road geometry. So, the exact curvature of the asphalt, the lane markings, the placement of traffic signs.
Right, that builds the world,
Yeah.
and then they use Open Scenario to govern the dynamic elements within that world.
Which means what exactly?
Well, Open Scenario allows developers to dictate logical parameters rather than hard-coding specific events. Instead of programming, a red sedan cuts the car off at this specific intersection, they program a logical envelope.
Okay, give me an example.
They'd write something like, a vehicle of X mass executes a lane change to the host vehicle's path with a time to collision of 1.5 seconds. The simulation engine can then run thousands of variations of that single parameter, altering the speed, the weather, the lighting conditions, creating a massive, closed-loop testing matrix.
Okay, so we have millions of virtual miles logged. The digital twin has survived every simulated multipath reflection and virtual rainstorm. But a mathematical model is still just a model, right?
Ultimately, yes.
Eventually, the code has to be downloaded into the physical Skoda ENIAC and tested on a physical proving ground. How does Audi VUT Bruno validate that their software logic actually translates to the real world?
They achieve validation by systematically eliminating the largest source of physical inconsistency, which is, of course, the human test driver.
Obviously. We ruin everything.
Pretty much. When you are validating software iterations, human variability destroys the integrity of regression testing. A human driver cannot physically execute the identical steering angle at the identical speed, braking at the identical millimeter twice in a row.
Right, because if version A of the software results in a smooth stop, but version B results in a harsh, sudden stop, you need to know definitively if the algorithm degraded or if the human test driver simply twitched their foot on the brake pedal.
Exactly. To remove that variable entirely, VUT Bruno equips the physical test vehicle with robotic steering and pedal actuators.
Like literal robots turning the wheel.
Literal robots.
Yeah.
These robotic systems execute the test maneuvers with a precision that humans simply cannot match. The presentation details that these actuators achieve a targeted speed accuracy of plus or minus 0.5 kilometers per hour.
That's incredibly precise.
It gets better. More impressively, they maintain a lateral deviation of roughly 2 centimeters.
2 centimeters of deviation on a moving vehicle.
Yes.
That means the robot can guide the 2-ton Skoda through a complex curve, and the tire will track within 2 centimeters of the target line, pass after pass. It provides a perfectly sterile, repeatable baseline.
It really does. You run the physical test with the robots, you map the telemetry, and you compare it directly to the digital twin's telemetry in the cloud. If the data aligns, the simulation is validated.
Wow. But, while the dynamic driving tasks require highly complex robotic synchronization on a track, validating the perception algorithms requires a radically different approach.
Yes, what's fascinating here is how localized and almost simple the lab testing can be.
This leads to one of the most practical, honestly kind of funny visual details in the entire source. The Institute has this multi-million-dollar cloud architecture calculating photon refraction and raindrops, right?
Yeah, it's super high tech.
But to confirm that the physical vehicle's camera hardware can successfully read and interpret a traffic sign, they just utilize a chassis dynamometer. They strap the Skoda ENIAC down in the workshop so the wheels can spin freely while the vehicle remains stationary.
Right, this setup allows the vehicle's drivetrain and wheel speed sensors to believe the car is physically moving down a road at speed.
And while the car is running on the dyno, the researchers simply position a standard flat-screen television directly in front of the vehicle's windshield camera.
Just a TV screen, yeah.
They play video footage of a road passing by and then flash an image of a speed limit sign on the TV, say, a standard 70 kilometers per hour sign.
And by monitoring the localized CAN bus we discussed earlier, they can instantly verify if the perception algorithms recognize the pixels on the television screen, categorize the shape and text as a regulatory sign, and pass that logic down to the drivetrain CAN to initiate a deceleration command.
It's so brilliant. It closes the loop entirely. You test the psychological limits of the driver in the DIL simulator. You test the decision-making logic against millions of edge cases using the digital twin in the cloud.
Then you test the vehicle dynamics on the track with robotic actuators.
And you test the hardware latency by essentially letting the car watch a driving video in a garage. Every single testing methodology is designed to verify the integrity of the overall software architecture.
Absolutely.
So, what does this all mean for you, the listener?
Well, I think it illustrates the sheer magnitude of the engineering required to safely remove the human brain from the driving task. To achieve that grandma benchmark, where a user can simply request a destination and safely arrive without intervention, institutions like WADI VUT in Brno must basically reconstruct reality in code.
Yeah.
They are calculating the localized voltage drops from a seat heater, modeling the Doppler shift of a radar pulse bouncing off a guardrail, and deploying robotic actuators to eliminate human inconsistency on the track. It is a relentless pursuit of mathematical certainty in a highly uncertain physical world.
So the next time your current vehicle gently nudges the steering wheel to center you in a lane, or triggers a little beep because you glanced at your phone, recognize the invisible infrastructure making that single moment possible.
It's easy to take for granted.
Acknowledge the 4,000 gigabytes of data processing in the background, the 25,000 variables continuously synchronized across localized networks, and the millions of virtual miles logged by digital twins to ensure that the logic controller makes the correct decision in the span of a millisecond.
The technological progress is undeniably staggering. However, reviewing the depth of this research presents a rather provocative conclusion regarding the future of mobility.
What's that?
The engineers at VUT Brno are proving they can successfully model vehicle physics, they can simulate complex weather degradation, and they can mathematically map urban environments. Yet the single variable that remains entirely resistant to mathematical modeling is us.
The human driver.
Exactly. The human driver remains unpredictable, prone to fatigue, and easily distracted. If the transition period of DCAS Phase 3 proves that the human failsafe is the weakest link in the entire architecture, the ultimate solution to autonomous safety might not be better driver monitoring.
It might just be removing the steering wheel entirely.
Yes, transitioning all of us permanently into passengers.
It forces a massive reevaluation of our relationship with personal transportation, doesn't it? When you look back at that historical photo of Fifth Avenue, the sudden influx of automobiles must have felt like a chaotic, almost insurmountable disruption to the people living through it.
It must have been terrifying for some people.
But the infrastructure adapted, the technology scaled, and the world moved forward. Reviewing the rigorous, localized testing methodologies currently being pioneered in Brno, it's apparent the foundation for this next great disruption is already being poured. Thank you for joining us on this deep dive. We'll see you next time.